So thanks for the introduction, and also thanks for inviting me. So it's always a great pleasure to come to Korea. Actually, this is my first time to KIAS, but of course not the first time to Seoul. So yes, so today I'm going to talk about an upcoming paper together with Jose Calderon Infante and Lucia Cordova. And Jose and Lucia are WARA postdocs at CERN, and Jose recently moved to Caltech, and then Lucia recently moved to Amsterdam, and also with Irene Valenzuela, who is a staff member at CERN. All right, so before starting the scientific part of my talk, let me just say one comment about the title of my talk. So as probably some of you already noticed, it's a kind of pun of a famous phrase. So if you didn't know about the phrase, you can just Google the original phrase, just dropping F from my title. And so, but unfortunately, we later found that actually we were not the first to make this joke. And when I Googled this phrase, with F, then I found this book, No Shift Sherlock. Well, I haven't read the book. Actually, I don't own a book. So I asked ChatGPT to summarize what the book is about. And according to ChatGPT, it's a story about a badass vampire hunter who is also a detective. So in case you're more interested about badass vampire hunter rather than quantum gravity, I recommend reading this book rather than listening to my talk. Okay, so with that comment, so let me start my scientific part of the talk. So basically this talk is about one of the swampland conjectures in quantum gravity. In particular, what is known as no global symmetry conjecture in quantum gravity. So people believe that there is no global symmetry in full-fledged quantum gravity, and this is supposed to be one of the most kind of solid swampland conjecture. There aren't many people who doubt the validity of this conjecture. And there are indeed many indirect arguments. The first one is based on perturbative string theory. So in perturbative string theory, whenever you try to construct some kind of global symmetry, you always end up getting some a gauge symmetry rather than global symmetry. And also there is an argument based on the black hole entropy as well. In more recent years, there are more direct argument using the ADS-CFT. The famous one being this paper by Harlow and Oguri, and also related argument was presented by Heckman, Hubner, and Murdia in 2024. So this argument basically uses, so these papers basically argue that the global symmetry in ADS quantum gravity is incompatible with the one of the kind of ADS-CFT dictionary, which is called entanglement wedge reconstruction. So I'm not going to go into the details of their argument, but let me just point out that this entanglement wedge reconstruction works only in the semi-classical gravity regime, where you have some ADS Einstein gravity. And this entanglement wedge reconstruction is actually expected to be modified by the stringy corrections or quantum gravity corrections. So in that sense, this was enough for proving the original form of the no global symmetry conjecture in semi-classical quantum gravity, but the proof is in some sense limited to the regime of the semi-classical Einstein gravity. So one natural question you can ask is, can we prove or argue for the no global symmetry conjecture in the full-fledged quantum gravity regime using ADS-CFT? So this is what my talk is going to be about, okay? So then one can think of how to show such conjecture, no global symmetry conjecture. So let me also clarify already in the beginning that in this talk, I'm only going to talk about the continuous global symmetry. Okay, so before talking about the global symmetry, let me remind you the famous fact about ADS-CFT, that instead of talking about global symmetry, if you talk about gauge symmetry in ADS quantum gravity, we know what it corresponds to on the conformal field theory side. So the gauge symmetry means that you have a gauge boson in ADS quantum gravity, and that is dual to conserved current on the CFT side. Okay, so this is a well-established dictionary of ADS-CFT correspondence. But of course, like what we want to understand is the absence of global symmetry rather than gauge symmetry. Of course, gauge symmetry is allowed in ADS quantum gravity. So you can ask what is the counterpart of the dual of the global symmetry in ADS quantum gravity. And if you think a little bit about it, then, well, you can convince yourself that unbroken global symmetry in ADS quantum gravity would correspond to some kind of global symmetry in conformal field theory. The basic reason being that if you have some like a topological operator which implements the global symmetry in ADS, you can also push it to the CFD side and get the topological operator as well. So this should correspond to some kind of global symmetry in conformal field theory, however, without a conserved current, because we don't want to have a gauge boson. So basically, like you have some charged operator, and the OP is consistent with like this kind of transformation, like a global symmetry transformation, but there is no conserved current, which basically gives rise to the charge by like a charge operator by integrating this object. Okay, so then like you can say that what is the CFD counterpart of the no global symmetry conjecture in the case of unbroken global symmetry, and then that is going to be this one. So you consider CFT with stress tensor T mu nu because you want to consider the quantum gravity rather than just quantum field theory in ADS, and the global symmetry G, but no conserved current corresponding to G. And we want to show that such CFTs are inconsistent. So this is a kind of like a claim that you want to prove. However, it turns out like proving this claim is a little bit difficult. Of course, like it would be nice to kind of show or establish this kind of claim using some conformal bootstrap arguments, but it is difficult because it is not so clear how to effectively use the fact that like there is no current in the bootstrap argument. So in the bootstrap argument, it is easy to implement the presence of the J mu because you just like need to kind of like put J mu in the OP expansion, but it's actually hard to kind of like impose the absence of J mu in the bootstrap argument. And one of the reasons being that like in the, well, either numerical or analytical bootstrap, it's difficult to distinguish a strictly conserved current, like a delta equal d minus 1 vector operator, and then almost conserved current, delta equal d minus 0.999 vector operator. And so this basically translates the fact that if you talk about this kind of unbroken global symmetry, and if you just talk about like operator, OPE of the local operator, it's actually hard to distinguish whether the symmetry is gauged or global. Okay, so well, this might not be obvious, but like at least as far as I tried, like this seems to be a little bit difficult. Mm-hmm. Right. So yes, I agree. Like there is one important difference between delta equal d minus 1 vector and a delta equal d minus 0.999 vector, which is the existence of the null state, or like basically conservation law. And I hope like maybe in the future we will find a way to effectively use it. But at the moment, I just say like I don't know how to effectively use it. Okay, but yes.
There's a complementary viewpoint.
Mm-hmm.
Good to see you. There's a complementary viewpoint on these issues too, from the point of view of more complicated topological contributions from the bulk, like multi-boundary problems, and from that you know, in a case like this, you would have selection rules on average, but with a non-zero variance that would be captured from holes and such.
Right. I agree. That's also nice. Yeah, that's also an important point. Although, like, I don't know how to uplift these arguments in the full quantum gravity regime because, like, we still need some gravitational path integral. Okay, but in this talk, I just wanted to point out there is actually one situation in which things are a little bit simpler, which is to consider spontaneously broken global symmetry. And the famous example being the shift symmetry, which corresponds to shifting the value of the scalar in ADS quantum gravity. And so the reason why shift like a spontaneously broken symmetry is easier, you can actually understand it also from the bulk. So if the symmetry or global symmetry is spontaneously broken, it's actually very easy to distinguish the gauge symmetry and the global symmetry. Because like if it is a global symmetry, you will have a massless scalar if you have a shift symmetry. Whereas if the symmetry is gauged, it introduces the Higgs mechanism, and you just get massless scalar. So you don't have any massless scalar. And furthermore, there is no remnant of symmetry. At least there's no obvious way to see the symmetry. And so and now I want to translate what they correspond to, especially the global shift symmetry, CFT statement. And so, as I said, a shift symmetry corresponds to shifting the scalar by some constant value. And so if you have some theory with a shift symmetry, then the theory needs to be invariant under this shift of the scalar. And in particular, this shift also changes the asymptotic value, so the boundary value of the scalar field in ADS quantum gravity. And in ADS CFT, we know that this boundary value of the scalar corresponds to coupling constant on the dual CFT using the famous ADS CFT dictionary. And in particular, and also I should point out that the fact that phi being massless thanks to the shift symmetry translates to the fact that this operator O due to this field phi needs to be marginal. So using this fact, you can actually translate what is the shift symmetry in ADS quantum gravity. So the shift symmetry in ADS quantum gravity corresponds to CFT with what I would call trivial conformal manifold. So there's a conformal manifold parameterized by this coupling constant, which is due to this exactly marginal operator O. But this conformal manifold is trivial because the theory is invariant, completely invariant under phi going to phi plus c. So which more precisely, on this conformal manifold, no CFT data changes. And so what we want to prove is that the conformal manifold cannot be trivial if you consider conformal field theory with stress tensor. So that's what my talk is going to be about. Okay, so far so good. All right, so let me also emphasize that. But before explaining how to argue this statement, the conformal manifold cannot be trivial in the presence of stress tensor, let me just emphasize the importance of having a stress tensor. Because if you don't have a stress tensor, if you consider conformal field theory without stress tensor, there are actually examples, well-known examples of the trivial conformal manifold. And the famous example is actually conformal field theory, some defect, what's called defect conformal manifold. So let's consider the conformal field theory with symmetry G, and then consider the situation in which conformal defect breaks the symmetry G down to H. And in this context, it is well known that the defect, conformal defect actually has a conformal manifold, and the conformal manifold is given by this coset, G over H. And furthermore, this is actually a trivial defect conformal manifold because every point on the manifold is related by a simple action of the bulk topological operator. So you consider some defect here, and if you push some symmetry operator, you can change the value. You can basically move from one point on the conformal manifold to another point on the conformal manifold. And because this is the symmetry operator, you can also shrink this operator in the bulk. And that corresponds to basically, that is the same as doing nothing. So that guarantees that this conformal manifold is trivial. Okay. And another example is to just consider free shift symmetric scalar in the ADS without gravity. And in that case, you are just talking about free shift symmetric scalar. So obviously the theory is UV complete in the bulk. And that corresponds to what's called a generalized free field conformal field theory, and which famously doesn't have a stress tensor. And then this one also has a very a trivial conformal manifold because this ADS theory has a trivial a vacuum manifold. So these examples show that the trivial conformal manifolds can arise in the absence of the stress tensor, but it is so the point of my talk is to show that trivial conformal manifold cannot arise in the presence of the stress tensor. Okay. All right. So this is the plan of the rest of my talk. So I will present the argument for no-shift symmetry in conformal field theory. And then I'm going to discuss some generalization to higher form symmetries. And then I'm going to conclude by making some comments and then talk about the future directions. Okay, so let's go to the argument for no-shift symmetry in conformal field theory. And so this is a general strategy of the proof. So the proof or argument uses a proof by contradiction in 2 steps. So first, we use a CFT bootstrap argument to show that one can construct what I would call like an identity conformal interface. I'm going to explain what I mean by this for any 2 points on a trivial conformal manifold. Okay, and then second, I'm just going to argue that existence of the identity conformal interface between nearby CFTs, which are related to each other by conformal perturbation theory, contradicts the structure of the conformal perturbation theory. And because this assumption led to a contradiction, then you conclude that the original assumption that of the existence of the trivial conformal manifold is incorrect. And then you can argue for the absence of the shift symmetry in quantum gravity. Yes. Okay. So let's first go to the first step. So in order to so what I want to show is that the trivial conformal manifold implies the identity interface. And to introduce the identity interface, I first need to talk about conformal interface, which was already introduced yesterday by Tatsuma. And so what is conformal interface? Well, actually, yeah, I think he discussed the defect, but I'm going to talk about a specific case of conformal interface between 2 different CFTs. So the conformal interface is basically some kind of like a defect or wall between 2 different CFTs, which preserves subset of the conformal symmetry of the original CFT. So you preserve like only SOD, 1 of the original SOD plus 1, 1, D plus 1, 1 symmetry. And this conformal interface also needs to satisfy several different crossing equations, which involve operators in the bulk and operators at the boundary. For example, if you consider a 2-point function in the presence, 2-point function of the bulk operator in the presence of interface, then there are 2 different OP channels. You can either fuse 2 bulk operators to get one like a sum of bulk operators, or you can just like fuse bulk operator to that interface and expand it in terms of like a sum of interface operators. And solving this constraint basically amounts to, well, like these crossing equations basically constrain the interface conformal data using the bulk CFT data as input. Okay? So once you know bulk CFT data, then you try to find a solution to the interface CFT data. And if you find one, then you can claim that there exists such an interface. And in particular, I should emphasize that in the bootstrap approach, solution to the crossing is basically the same as like a constructing interface. Of course, like historically, like when people talked about conformal interface, people kind of started with some microscopic description based on the Lagrangian, and then tried to impose some boundary condition. But in a more modern bootstrap like a philosophy, we shouldn't rely on the like a microscopic Lagrangian. So the construction of the conformal interface corresponds to finding solution to the crossing equation. Okay. So now let's talk about the trivial conformal manifold. So on a trivial conformal manifold, by definition, conformal field theory 1 and the conformal field theory 2 share the same bulk conformal field theory data. So the CFT data in the bulk is exactly the same between CFT1 and the CFT2. So as long as we care about the solution to the crossing equation, you can just like first you can just replace CFT2 with CFT1 because the bulk CFT data is identical. So that means that actually there is a one-to-one correspondence between interfaces within the same CFT, CFT1, and the interfaces between CFT1 and then CFT2, which are on the same trivial conformal manifold. Okay, so there is a one-to-one correspondence with this setup and this setup. And in particular, if you talk about the interface within the CFT1, there is a kind of like always an obvious one, which is called identity interface, that corresponds to basically inserting nothing between 2 CFT1s. And because of what I said, there should be a corresponding solution also on this side. And the interface CFT data between CFD1 and CFD2 is basically identical to the interface CFD data of this identity interface between CFD1s. Okay? So now I'm going to argue that the identity interface between like a nearby CFD, CFD1 and CFD2 are incompatible with the conformal perturbation theory. So this is a rather simple argument. So let's analyze the identity interface between nearby CFD, which are related by infinitesimal deformation induced by some like exactly marginal operator O due to the field phi in the bulk. And so this identity interface, at this point, we don't know the microscopic description, or we don't know the description in terms of conformal perturbation theory, but what we certainly do know is that on this side, there is an integral, like a bulk integral of this operator, or exactly marginal operator. And on top of that, at the infinitesimal level, it might involve some deformation localized at the interface, like integration of the operator with dimension d-1, precise only at the interface, for example. Okay? But one thing that's important for us is that no other deformation away from the interface is allowed, because if you do some other deformation away from the interface, that's going to be detected by the stress tensor conservation law. So this is like why having stress tensor is important. So there are like several different ways to see the importance of a stress tensor. But this is, I think, the simplest way to see the importance of the stress tensor. So to summarize, yeah. Exactly. So position dependent like integration of the bulk operator was discussed in some of the literature, but that is not allowed here because of the stress energy tensor conservation. Okay, so to summarize, we expect that this identity interface in the kind of conformal perturbation theory regime is going to be given by like integral of this exactly marginal operator in the bulk plus something that you can do strictly on the interface. And then the rest of the argument is actually rather simple. So one thing you can argue for is that if you consider this just a half space deformation of this operator O, then this half space deformation turns on the 1-point function of O, because like at the linear level of the perturbation theory, like evaluating this O corresponds to just evaluating integral of the 2-point function, and then that which gives a non-zero answer. So this obviously is in contradiction with the identity interface. But of course, like we cannot end the proof or argument here because there can be some other deformation localized on the interface. But however, for example, if you consider this deformation of the integral of the dimension d-1 operator precisely at the interface, then at least at the first order in the deformation of delta rho, the interface coupling constant, the situation is the same, because like if you compute the two correction to the 1-point function, that amounts to evaluating the integral of this 2-point function. But these two operators have different conformal dimensions, so the 2-point function is 0. But then, well, you can argue like what happens in the higher order in this like interface coupling. And it is true that at higher orders in the interface coupling, there may be some contribution to the 1-point function of O, because now you are supposed to evaluate a 3-point function of O, O prime, and O prime, which is in general non-zero. However, but even if that happens, and if it gives some non-zero answer, which cancels this value, but then one can instead consider the 1-point function of O prime. And then because of this deformation, now 1-point function of O prime becomes non-zero, okay? And which again leads to contradiction with the fact that it's identity interface. Because I didn't emphasize this point, but if it's the identity interface, the solution to the CFD bootstrap is the same as solution to the CFD bootstrap between CFD1 and CFD1 with inserting nothing. And if you don't insert anything, the 1-point function should always be 0. So the non-zero 1-point function contradicts the assumption that you have an identity interface. So to summarize, like whatever you do, one can argue that there's a contradiction to the identity, to with the identity interface. And in particular, you can even talk about some non-local deformation localized at the interface. But so in that case, like it's a little bit hard to exclude them by using this kind of argument. But there is another argument based on the displacement operators, which basically like excludes having such a deformation. Well, so exclude the identity interface with such deformation. So to summarize, so one can argue using this argument that the identity interface is incompatible with the conformal perturbation theory. And because the assumption of the shift symmetry led to the identity interface, and then identity interface led to a contradiction with the conformal perturbation theory, so therefore we conclude there shouldn't be shift symmetry in ADS quantum gravity. So this is a recap of the argument. So we first use the CFT bootstrap to construct the identity interface for any 2 points on a trivial conformal manifold. And then I argue that the existence of the identity conformal interface between nearby CFTs contradicts the conformal perturbation theory. Okay, so any further question at this point? Okay. Yes.
Sorry. Still thinking about exactly what to say. There should be some relation of this to Janus.
Mm-hmm.
Like the bulk avatar of this would be what you would actually get in the bulk if you were to your interface from a bulk point of view is going to be some domain wall that interpolates between two different boundary values of your scalar and this.
Right.
Like there, a Janus background, you have back reaction, you get 1-point functions, you get all the same things that you're saying you would find here.
Yeah. Yeah. So let me think. What's the best way to answer your question? So, right. Yeah. So I think like this universal answer that I showed should correspond to Janus setup, and basically this CFT argument is saying that like having something like Janus is kind of the only possibility that you can have in the bulk. And so what's not so clear just from the bulk argument is that being forced to have Janus forbids the shift symmetry. Of course, like if you start from like a top-down example, of course, there is no shift symmetry to begin with, and you can construct Janus. But then like you can argue that having like if the only interface that you can construct in the bulk or only domain one that you can construct in the bulk is Janus, does it imply that there is no shift symmetry? So that part is not clear from the bulk, but from the conformal field theory argument, you can argue for that.
Thank you.
So yeah, so actually that was a very good point. So maybe like in the way that I presented the argument, the second point, like a second step seemed more important. But actually the first step is actually like quite non-trivial from the bulk point of view. Because what I was showing here is that, what I was showing here is that if there is a trivial conformal manifold, which is a direct consequence of the shift symmetry. So what I'm showing here is that if there is a shift symmetry in the bulk, you can construct the identity conformal interface. But the contrapositive of this statement is that if you cannot construct the identity conformal interface, there is no shift symmetry. So that part is non-trivial from the bulk point of view, yes. Another question here.
So your argument uses conformal perturbation theory.
Mm-hmm.
Could it be that you have something that's 0 to all orders in conformal perturbation theory, but the actual answer is non-analytic in the coupling, and so?
Okay, so it is right. So it is okay. So let me make two comments. So it is true that we are assuming the convergence of the conformal perturbation theory, but what we are showing here is that already at the first order of the deformation, you get non-zero, and you cannot fix it. And as long as the conformal perturbation theory is convergent, this argument is robust. And let me also say that so we are used to the fact that a perturbation theory in quantum field theory is not a convergent series, but that's because we are used to the perturbation theory around a free point. And then generically, at least in many examples, if you start from some point in the bulk of the conformal manifold, actually conformal perturbation in many cases seems to be convergent. And it seems like a conformal perturbation theory is asymptotic only in some sense, like infinite distance points.
So you say there's nothing like an e to the minus 1 upon delta phi.
Sorry.
I mean, there cannot be an effect which is like an exponential, like an essential singularity.
Right. So, yeah, right. It's true that so typically if you have a asymptotic series, the point that you're expanding around is a kind of essential singularity, and then you cannot go in various directions. But if you start from some a bulk point in some point in the generic point in a conformal manifold, you can go in both directions.
Be true everywhere on the conformal manifold.
Sorry.
This expression that you have would be true everywhere on.
That's true. So, yeah. So I cannot say immediately whether this argument fails at the infinite distance points. Yeah, okay. But yeah, so I don't know if the argument fails at the infinite distance point or it still holds, but yeah, let me just say. But we still need to use use the fact that the conformal perturbation theory is convergent to argue for the validity of this argument. Okay. So now let's move on to the second part, unless there are further questions, which is the generalization to higher form symmetry. So let's talk about the generalization to higher form symmetry. So to be concrete, I'm going to talk about one form symmetry of Maxwell theory, so which corresponds to these two kinds of conservation laws. Well, I guess if you work with generic D, then this should be the one that we need to talk about, because the other one corresponds to D-3 form symmetry. And so if you just consider free Maxwell theory without any charged operators or charged scalars, these symmetries are exact. However, in ADS quantum gravity, these symmetries are expected to be violated by the presence of charged particles, and which is related to another Swampland conjecture called the completeness conjectures. And so the question that we can ask is that, can we show the absence of one form symmetry of Maxwell theory in ADS quantum gravity using a similar arguments? And so what I'm going to do now is to kind of give a sketch of the generalization of the argument that I presented before, which was about zero form symmetry. So the starting point is as follows. So if there were electric one form symmetry in the bulk, then one can construct the codimension 2 topological interface in ADS. So you can construct this kind of codimension 2 interface on which you integrate a star F. Okay, so this is a symmetry operator for the one form symmetry, and then so because this is a topological operator, and you can just shrink it in the bulk, and so that's why this is equivalent to the setup in which you don't have this codimension 2 topological interface. Okay, and by pushing this topological interface to the boundary, we get some interesting object on the conformal field theory side, which is called a monodromy conformal defect. So the way that I push is you consider this setup, and then you push it like this. And if you push it like this and then just view this setup just from the CFT boundary point of view, then you get this object. So this is a kind of, this blue circle is a codimension 2 defect on the CFT side. But so this looks like a codimension 2 conformal interface on the CFT, but it's actually not like it's a little bit special conformal defect because in the interior of this codimension 2 defect, you need to integrate this exponential of star j, which came from this one. So this is just a direct translation of f to j using the ADS CFT dictionary, where j is a conserved current. And so as I said, this one-form symmetry operator in the bulk, one-form symmetry operator in the bulk is topological. So that also means that this monodromy conformal defect on the CFT side should also be topological. So nothing should change when you change the shape of this defect. Okay? So then what we need to prove is that something like this cannot happen in theory with stress tensor. And the argument is again very similar. So we consider this the regime in which this alpha, the parameter of the symmetry operator, is much small, much smaller than 1, and you use the perturbation theory in alpha. And in that regime, one can show that the monodromy defect turns on one-point function of J mu, because now you are expected to evaluate this two-point function, and which is non-zero. And again, the fact that it turns on one-point function is in contradiction with the fact that this should be a topological defect, because if it's a topological defect, you can just shrink it and then annihilate the entire defect. And of course, as in the case of zero-form symmetry, we also need to argue that this non-zero one-point function cannot be fixed by any other local deformation localized at the codimension 2 interface, which codimension 2 defect, which is basically this blue circle. But basically, the argument is very similar, and you can argue that this cannot happen. And because of that, you can argue that topological monodromy defect cannot arise in conformal field theory. Yes?
Bugging me for a while. So you said at a few points that if you had a topological operator in the bulk, do such things even exist? And once we include the coupling the gravity, isn't that
Right. So yeah. So I have one slide right after this, but let me just make 2 comments. I think that there are several issues. The first issue is some topology change in gravity. So typically, people say that there is one argument why topological operator cannot arise in quantum gravity is that in full quantum gravity there can be some topology change. So it doesn't make sense to talk about a topological operator at all. And if if that's the argument and you accept, then we don't need to talk about this at all.
But in effective field theory, it works.
Right.
Even with perturbative gravity.
Yeah, even in perturbative gravity. So indeed, there was a recent paper, especially by Ibu Bar, which points out that even in perturbative gravity, there is a problem in defining topological operator corresponding to the symmetry operator. So let me go through this slides. So there is one caveat in particular for this argument for the higher form symmetry. So the caveat is that the argument for higher form symmetry only shows the absence of topological symmetry operator, topological operator in ADS quantum gravity. But strictly speaking, in quantum gravity, the absence of topological operator is not exactly the same as the absence of symmetry. And let me explain why. So in quantum field theory, we are kind of used to the fact, especially this is a point of view advocated in this paper, a symmetry is basically synonymous to the existence of the topological operators. So this is how people generalize the notion of symmetry to a higher form symmetry and a non-invertible symmetries. However, it was pointed out recently that these two notions may not coincide in quantum gravity. And in particular, if you just talk about the presence of the topological symmetry operator, there is actually an obstruction for constructing topological symmetry operators already in the gravitational EFT. So this is already like an obstruction in the effective field theory. You don't need to talk about the UV completion. So the argument is basically the following. So this argument was originally presented by these authors, and then there was a follow-up argument also by these authors. So the argument that goes as follows. So let's say you want to construct a topological operator by exponentiating the conserved current. So this is a typical form of the topological operator. But if you really want to make sense of this kind of expression, you need to make sure that like this operator is like well defined as an operator in quantum field theory. And in particular, like if you expand in powers of alpha, the first term is okay because it's just an integral of the local operator. But in the second term, there is some like a coincident point singularity because you have like two integrals. And strictly speaking, you need to regularize this object. And so these authors discussed like how to regularize this object. And so we really need to introduce some. So one way to regularize is to introduce some kind of thickness to this like a topological operator, and then like later take the limit in which this thickness goes to 0. And then this procedure works perfectly for quantum field theory, and then you get back to all the properties that you want for a topological operator. However, they pointed out that in gravity, this limit is a bit problematic because the gravitational back reaction becomes like infinite in this limit. So that's why like they argue that they cannot be like there's an obstruction for constructing the topological symmetry operator in gravitational EFT. And however, their argument does not exclude having other notions of symmetry like a word identity or conservation laws. So what they showed is that like basically what they argued is the kind of like absence of the symmetry operators, but they didn't exclude the possibility of having other notions of symmetries. So to summarize, like we need to be very careful in quantum gravity, like what notions of symmetry we are going to use. And so in that sense, like there is a bit of weakness in my argument for the higher form symmetry because I basically relied on this notion of symmetry. And then what we only showed is that the absence of the topological symmetry operator. But let me also emphasize that like for the argument of the shift symmetry, we didn't need to rely on this notion of the symmetry because we basically first translated the concept like a shift symmetry in the bulk into the trivial conformal manifold, and we just like use that to exclude the shift symmetry. So in that context, we didn't like need to rely on the topological operator base definition of the symmetry. Okay, I hope that point is clear. But so yeah, please ask me more questions if something is not clear. So I want to make such a claim, but at this point I cannot because of this. Because what I showed here is that like absence of topological symmetry operator, but that doesn't immediately imply the presence of the charged operators. Okay, so let me conclude. So we are a bit ahead of time. So I presented the CFT-based argument for no shift symmetry in ADS quantum gravity, and also like I presented a generalization to higher form symmetry. And so there are two things to emphasize. Like so the argument works beyond the semi-classical gravity regime. So that's kind of like a new point as compared to the previous arguments. However, so far it only works for spontaneously broken symmetries. So there are few future directions. So the first one is like remove this caveat that I talked about in these slides for higher form symmetries, and to really establish the presence of the charged particles. And of course, like it's also important to talk about or generalize the argument to non-spontaneously broken symmetries, which seem a little bit harder. And you can also ask like whether this kind of setup, for example, like interface or monodromy defect may be useful for other swampland conjectures, for example, the weak gravity conjectures, or no -1 form symmetry conjecture. And And indeed, like we recently found that like this interface is also useful for discussing absence of the -1 form symmetry. And so one thing like I want to emphasize through this talk is that like a starting interface, well, in particular, the monodromy defect seems like rather important for addressing swampland conjectures from ADS-CFT. So there may be some other application of monodromy defects in the context of swampland and ADS-CFT. Okay, so let me end here.
Please ask questions.
So is there a reason why you don't have discrete symmetries in the outlook? Is that hopeless or?
Oh, so the reason why I didn't put discrete symmetries are because like the argument uses like infinitesimal deformation. So it'll be very nice to talk about this discrete symmetry, but probably the argument is going to be very different.
Thank you.
Any other question?
Since you are working from CFT side, I mean, we do sometimes do so-called bottom-up holography. I mean, do you have a statement there too? Not necessarily string. So
not necessarily. Could you repeat the question?
I mean, if this is entirely CFT argument,
Yeah.
I mean, this would be applicable if somebody want to build, say, some bottom-up version of holography. You think that's the case?
Yeah, I would say so. Yeah.
Because it sounds very strong statement. I mean, string, I guess we sort of expect this to happen, but I mean, so-called bottom-up holography sounds like much bigger space, bigger sample. So, I mean, if somebody sort of suppose my student wanted to came with holographic model, gravity model with some global symmetry, should I reject him immediately?
Yeah, I would say so. That's the point of swampland conjecture, I guess. Well, of course, like here I'm assuming that like that quantum gravity theory should correspond to some kind of well-defined CFT, like a single CFT. If you allow yourself to talk about some kind of average CFT or something else, then maybe like things are a little bit different.
Is there any other question? If not, let's thank speaker again.